All right. Let me just turn my, okay, we'll do that. I figured it out. All right. Well, you guys couldn't hear it, but the guy is basically saying, I'm Yusuf Ashktorab and welcome to my kidney presentation.
Blow up, Yusuf.
Blow up, blow down. What the hell? Nah, that's not right. All right. But yeah, I use VO3, Google's model to make that. I thought it was fitting because it's an AI presentation. So let's get into it. I got to go really fast because is it going to? Okay, so the outline, I'm going to talk about who I am, the fundamentals of AI, how we're using AI in nephrology, addressing the concerns of AI in medicine, and then some overall tips of how to use AI in nephrology. So who I am. Let's ask my own AI bot who I am. I made this on my website, which I can have more information about after we finish if we have time. But this is just an excerpt from my website. It's just a GIF. But basically, I'm Yusuf. I'm a second-year med student at Howard. I'm working with Suchi and Maria this summer on CKDU and applying AI to it. And I'm very interested in AI in medicine, and I'm here to talk about that. So that's who I am. Basics of AI. So when I asked ChatGPT to explain the basics of AI, this is what it gave me. So yeah, don't look at it because it doesn't make sense. So that's the point, is like, it's not as easy as you guys think it is. There's all these terms people throw around and you're like, what is actually going on, right? So we're gonna start off with AI, just the fundamental definition. So John McCarthy, he was actually at Stanford. He was one of the people who had one of the main definitions for it, and just science and engineering of making intelligent machines, especially intelligent computer programs. Note that this is not just like AI in the sense that we think of it. It can be an if-then statement. It can be simple algorithms depending on what you define it as. So yeah, AI could be simply an if-else statement. So what's ML, or machine learning? So machine learning is the subfield of artificial intelligence that allows computers to learn and improve from data, right? So you're giving it a data set and it's learning from that. AI in general, now this is a subfield. So machine learning has a couple of subfields as well. This is not all of it. These are just four main ones I wanted to talk about here today. So let's start off with supervised learning. So supervised learning is when you give the model input-output pairs and you label the data set, right? And then you have the model trying to predict those labels. So for example, if you have a data set of chronic kidney disease patients and you give it age, eGFR, lab values, and you have labels. This person had CKD, this person didn't have CKD, and you predict that. That's supervised learning. That's what a lot of machine learning is. That's even linear regression, logistic regression, more complex things that random forest, XGBoost, et cetera. The list goes on. Most of it is supervised learning. Now let's go to unsupervised learning. So unsupervised learning is when it just finds patterns based off of unlabeled data. So let's say we threw that same exact data set that we had, but we didn't label the CKD or not say CKD, and we just asked it to find who clusters together. So something like k-means could find clusters, and this could be for finding hidden subphenotypes of a disease, for example. And we'll talk about some examples of nephrology there. So this includes UMAP, PCA. Then we have reinforcement learning. So this is really cool, but it's not used as much in medicine. And the reason is the model actually has to apply its decision in real life. So the model will make a decision, interact with the environment, and learn from that decision. So a prime example is like Instagram Reels or TikTok. You guys go on that all day. Well, it's learning from what you spend more time on and what you don't. So when you spend more time, it will get that as a positive reward, and it will keep updating its weights until it finds the perfect thing. This could be used in medicine, like for example, if you have drug dosages and whatever, and once you give it, it'll get the feedback. You can't really use it. The only way you can do this. Dr. Ahmad did not do this. I think you did. Okay, so basically, it's learning from its actions, and in medicine, you can't just let a model decide a patient's fate, right? So people do this by simulating things and trying to see what the model can do based off a simulated environment. But this is the hardest thing, and they don't really apply it as much.
Wait, Yusuf, can I ask you to, I told you we would interrupt.
Okay,
One slide back to the unsupervised learning. So when you do the clustering, what rules exist to test whether the clusters are just random versus, because when we have big data,
Yeah.
you could just have false
Yeah, so
clusters, right?
unsupervised learning is like really an art. Like a lot of it is just for visuals, like you see in UMaps. In a UMAP is like one of the main figures you see in like genomics research, where they throw like millions of genes into a thing and
Right.
they make these things and they cluster the cells, right?
Or
A
like
lot of it-
amines I've seen.
Yeah, so a lot of it isn't, it's really hard to find a meaningful outcome. That's why you can go look at the clusters and you can see the individual features that are high in that cluster. So like if you see one cluster has a high amount of X lab value, whatever, you can kind of define some meaning to it and see what's going on. But it's more of an art, is what they say.
But it's the same as supervised learning. We use the same measures. So with the same data, right? You can say, okay, I know I have labels CKD and no CKD, but now I'm going to feed in this data without labels,
And let's
right?
see
Yeah.
whether it
So then you can
matches.
still calculate the sensitivity, positive predictive value, the ROC calculates the C-statistic, just like you do with any other model.
But it's,
You
but
just don't use the labels. You let the data tell you what is happening.
But there are fields like Yusuf is mentioning where there are no labels
Yes,
because it's
it is
discovery,
possible.
right?
Yeah, and then
So-
it's discovery.
Yeah.
Right, so the metabolomics or the
Yeah.
proteomics that Snyder Lab does, for example, they just have a bunch of cytokines or a
Yeah.
bunch of proteins, and they're looking for signals, but they get criticized because many of those don't actually.
It's
I mean, they may
it's all
come up
discovery.
with something, some association with something, but ultimately does not really clinically change.
Ultimately, yes, but the basic index they use is basically how much, this is a very abstract concept, but how much the variance is different between clusters. Like this is how the algorithm defines different clusters, and you set the limit. Like there is no objective thing. Like if the variance inside clusters divided by outside clusters is above a certain limit, then
Then
you
it's a true
decide this
cluster.
it's a cluster. But what is that limit? No one knows. Is it the same across different data? Again, no. That's why it's kind of criticized.
Got it.
Right.
But also that ultimate, whatever signal they find, for example, like there was something that I read about pregnancy and going into labor as a signal, it was never borne out in prospective.
Oh yeah.
Yeah,
You can
right,
validate
so-
it in prospect and you may find
you don't
nothing.
find it,
Yeah.
right,
Yeah.
exactly.
That's just what you have to do, right?
Right.
Even if you find it with something, it's like the validation that you do even with supervised learning, because you know the models do better in the data that they are trained on.
Right.
Right, so the real test is what happens when you go out of sample.
All right, self-loop supervised learning. So this is what's used like in training LLMs and different things. So it's when the model itself makes its own labels. So like, especially with like words, for example, the patient has an EGFR, whatever, stage 5, you could block out the 5, the model would block out every word and continue testing itself until it finds the best parameters to test that, right? So that's kind of used more in deep learning and LLMs. So the next thing is DL, deep learning, right? And deep learning is where you're using neural networks now. And these are for more larger data sets, lots of data, especially used with like images, like so CNNs, convolutional neural networks, those are really using images. And you start out with a couple of inputs and these neurons connect to each other. And then you get the hidden layers and the output layer, and the hidden layers. One of the things like these are why they call black box model, because a lot of these large language models are making all these layers, but you have no idea why, like you don't know what's going on. So it's kind of harder to understand. And then we have generative AI. So this is just kind of like its name, like generating new content. So instead of just classifying something as rapid decline or not rapid decline, or you'd be actually making new words like an LLM, or creating something new, could be images, words. And then you have foundation models. So foundation models are just really large models that have multiple purposes, like ChatGPT, for example. It can do anything from write an email to write some code to do whatever. These can be image models that can make any type of image. So it's just a broad term for models that can do a lot of things. And then more specifically, you have LLMs, so large language models, and these are for text generation and understanding, and these are what we use every day with ChatGPT, Gemini, etc. So, okay, so now we're gonna get into some terms. So fine tuning versus retrieval augmented generation. So I'll start with RAG, retrieval augmented generation. This is when you kind of give like an LLM some external documents or logic, for example, a textbook or something, and that LLM will use that in all of its responses. It will kind of fact check itself. This is how you can get a more updated LLM. And this isn't the same thing as just giving the textbook inside your prompt. It actually encodes it in a vector, and the model will use that every time it does it. So people have done this actually in nephrology. I don't know. They basically created a GPT, like you know how you can create GPTs in OpenAI, and they gave it the KDI-Go guidelines, and they called that a RAG. I'm not sure if that's actually a RAG, but it got published, so I guess it is. But basically, you can do this. And then fine tuning, it depends on what you're talking about, but in LLMs, you can just train an already made model on new data to tune it to what you want. And that's actually changing the weights. So in RAG, you're not changing any of the weights. You're just adding an additional vector. In this, you're changing the weights. So that's like making BioBERT from BERT, or you can make a nephrology-based model if you train it on nephrology things. So how do we evaluate AI models? So note that these 4 terms I'm talking about traditional machine learning models, so like logistic regression, random forest, these things. So you have the ROC AUC, the receiver operating characteristic under the curve, and area under the curve. And this is kind of for the different classes, and 1 would be perfect classifier, 0.5 would be random guessing. This is kind of like the golden thing people use in their papers to determine how good of a model is mostly. And then there's some other terms in machine learning, like precision is what they call positive predictive value, and recall is what, or sensitivity is what they call recall. So it's just reusing terms for some reason. And these are very important in these models. And the F1 score is a harmonic mean of the 2. And that's a really good score because, for example, in our application of CKU, which I'll talk about later, like we can get a very good ROC AUC, but it would just be the model just predicting no for everyone because we have such low cases, right? So you have to be careful when you just look at the ROC AUC, you have to look at everything. And then for evaluating LLMs, there's a couple of things. One interesting thing is AI is a judge. So you can use, okay, let me explain this. I used AI to make an AI judge, which is judging an AI, basically. So AI can judge AI. And this is the paper from IBM Research where they made this tool that can judge AI based off of whatever your rubric is, and it's being used a lot now in research. And if you notice, this is the same last name as me because it's my sister. So yeah, I just shout out to my
Wait,
sister.
yeah, can we go back? You're going super fast and this is
I'm
great,
sorry, I'm
but
sorry.
we need to go back to the, where
Which
you were
one?
talking about the precision recall.
Okay.
The F1 score. Can you explain that a little bit more? It doesn't sound like a calibration slope, right? No. So what is this?
I think it's like both of them squared divided by 2 times both. I don't have the exact formula on me right now. But the point is, it's like a combination of the 2, so you can have a really good, you already know the trade-off between precision and recall, right?
Right.
So it's kind of a combination of both of them. So your model might have really good recall, but horrible precision. That will be
So
just,
Is this like a Uden index thing or like that? Like trying to find.
I have it in my notes.
No, I Googled it. 2 times precision times recall divided by precision plus recall.
But,
Yeah.
but I get the formula, but what does it help us in terms of decision making?
It's like for both of them, right? So like your model could have really good recall if it's predicting yes for everyone, and you might
Right.
have a lot of cases, you might have a class imbalance, so that might be also a good ROC AUC.
Correct.
But then you look at the F1 score and it
And
sucks because
because
the
there's
model
no
sucks because it's just predicting yes for everyone. The same goes with the no example in our case, right? Our F1 score in the initial models was horrible because it was just predicting no for everyone because it had literally 0 recall,
So
right?
it's on the ROC curve, it's like.
No,
It's
it's
not nothing to do with ours
Nothing.
because.
You know, this basically,
Trade off.
oh, sorry.
sort of a bias.
No,
right?
this is basically the reason this is defined. This is just for machine learning algorithm. This was defined because machine learning algorithms need a singular index to work with. And as he said,
Optimize.
yeah, they cannot work with recall alone. They cannot work with precision alone. So we need something that combines both. So it doesn't
Precision
mean
is actually
anything. It's
positive.
just used for machine learning
It's
algorithms
okay.
so that they
Got it.
can, but
But
they
it
can't refer.
shouldn't be really used for clinical decision.
No,
making
it's
like
not.
we do for sensitivity.
No, it's not. It's not even defined for that.
Okay, got it.
Oh, okay, this was a paper from Apple last week, and they basically said that AI can't think because you know how they made these reasoning models, right? These LRMs, and they're saying, oh, AI can reason now, and it's showing the reasons. And these people at Apple made a game that had to do a lot with thinking, and they ran the models through the game, and they realized because the models weren't trained on the game, they literally weren't able to think through these scenarios. And they basically came to the conclusion that the model was taking, instead of working from A to B, it was picking answers and try to find the solution. And it was they basically said these models are just pattern, they just find patterns. And my take on this is like, it's kind of interesting because I think, okay, who cares how the model is getting there? If it's getting the correct solution, sure, it's a pattern thinker, but it's an interesting perspective and people have opinions about this, so I wanted to share that. Okay, so we're gonna talk about AI agents, right? So this is like the hot topic now in AI. They're all talking about AI agents. All the startups are agent for this, agent for that. Everyone's changing AI to agent in their website because they want to be relevant. But the truth is, we've all been using AI agents for a while. We just didn't know. AI agents basically are built around LLMs, and they allow the LLM to interact with the environment. So instead of, for example, saying, hey, I want to book a trip, and telling it to ChatGPT, and ChatGPT would respond with instructions for booking the trip. You would say, hey, I want to book the trip. The agent would now, around the LLM, give it tools, access to your calendar, access to the weather, access to where the best place is, the prices, and the LLM would actually go and book the trip. So it's basically something that will take all the tools you have and continuously try to get that goal done while learning at the same time. And so this is kind of the new hot topic. And so AI agents are in medicine, but they're not using the term agent because I guess they're made before the term agent, or it's not like a hot term in medicine, but it is a hot term in AI. For example, Viz AI is basically this AI agent that is constantly reading CT scans in the hospital. And the second it sees a stroke, it will automatically notify all the doctors via their phones to go and act on it, and it saves lives, right? And it's an agent because the human doesn't have to give it the data. It's constantly looking at the data, it's making decisions, and it's interacting with the environment. Even like the term AI agent has very interesting definitions. So people have different definitions, but some can consider the AI scribe that now is in the clinics at Stanford as an AI agent because it's constantly listening and it's responding and it's writing the notes. So we're using AI agents. AI agents are going to be in our future. Technically, there are AI agents in nephrology. This is like some random startup I found, but it's interesting. It's called Nephrolitics, or Saya by Nephrolitics. They basically made this thing that integrates with EMRs in nephrology clinics, specifically for nephrology clinics, getting all of the patient data and giving real-time assessments, notes, etc. So it's pretty interesting how people are applying AI to nephrology. So we're going to talk about some use cases in nephrology. So check out this image. This is a Sri Lankan guy holding a kidney and AI and CKDU, right? So I know there are some people in this call.
Website.
Yeah.
For sure.
Yeah, so I know there's some people in the call that don't know what CKDU is. It's basically chronic kidney disease of unknown etiology. So we don't know what's going on. And the one we're focusing on is in Sri Lanka, and they don't have hypertension or diabetes. And so I'll talk about it more here. So this is our team in Sri Lanka. Great people doing the work for us. And then, so now we're going to talk about the design of the study. So basically we have two. We have the KIP study, which is patients who already had chronic CKDU, and we've just been following them over time to see what happens to them, right? And so we we kind of filtered them out because we wanted to make sure they had the condition. So we want to predict a condition, which is EGFR less than 15 after a certain amount of time. So we don't want them to have it before 2019 because that would mean they already had horrible kidney function and our model means nothing. And then we also wanted to have enough records. So this is what happened. Now, this is going to be a cool slide because Maria made this nice flowchart and I just put it into ChatGPT and I made this one. But the cool thing about this one is ChatGPT gave me the code with Python. So now whenever I want, I can go and change the colors, change the values, change everything. And you guys can do this in your papers with anything that you want to do. So it's pretty cool.
Actually, can you go back? Because the initial one, I actually did it on paper. I took a picture, I uploaded the picture to AI. And
So
gave
AI.
me- And he just created a push chart for me, and it gave me a website that I could go to with the code for that website, because I don't know how to use Python. And so then I could change it and added more stuff as I went along.
Wow.
And then I use AI again on her AI
Yeah.
application to make a better AI version. So yeah, so this is something you can do with a lot of things. It's cool, so I wanted to share it. This is just one of the patients and their EGFR over time. This is kind of just to show that it's very complicated. It's not as simple as one patient having horrible EGFR slope and one patient having stable, and patients are all over the place. So a simple just linear plot like OLS isn't going to do the trick. So let's talk about what we are doing with AI on CKD. So first we have supervised models, right? So what we're doing is we're trying to predict through supervised methods like random forest, XGBoost, etc. If we can predict these patients based off of their initial period or baseline labs, right? Can we take this initial patient who's enrolled in our study and see, are they going to develop CK or a worse version of CKDU? Are they going to be a rapid decliner, right? So this would be helpful if we were able to figure this out because we can intervene, right? So now we have unsupervised models. And this is again very useful here. And this is actually an actual plot that I ran on our patients. Basically, we don't know what a rapid decliner is or isn't, and we don't know what defines the groups. Are there hidden phenotypes, etc.? So we want to use unsupervised models and see, are there any patterns we don't see? Are there certain patients that are grouping together and having this worse kidney function, right? So this would be a great help, and we've applied that. And then finally, LLMs, right? So we're using the SecureGPT by Stanford, which is good for PHI data. And we're basically going to give it the initial info that we gave to the supervised models and see, does GPT have any reasoning that's of value, right? Because it's pretty interesting what these models can do. And we want to apply LLMs too. So we're basically attacking by all AI methods. And yeah, this is one of the pictures I had. It was cool. It's just like a random forest on a kidney. I don't know. This was Google's AI model. So AI CKD itself. So yeah, so there's this model called Kidney Intel X, and they use it to predict DKD progression. And basically, the cool thing about this model is they use random forest for this. But the cool thing about this model is they applied it in the real world. They implemented it in the EHR. So this was at Mount Sinai. And this model was implemented in the Mount Sinai healthcare system. And it saved a lot of money, right? Because these models are expensive to make, but they save a lot of money. So, there's always a thing AI costs a lot, but in healthcare, it can save a lot. If you can predict someone is going to have a worse outcome and intervene and save the money that you were going to spend on all these patients, it's a really good outcome. So the
question, how did I save money? What was the intervention?
Yeah, so the model was predicting who was gonna like from initial stages, it was gonna predict who was gonna have DKD with like a worse outcome, and even at primary care level, etc. And it would tell the physicians about this, and the physicians would act and give whatever drugs, etc., that would be beneficial. So instead of letting the disease go its course and these patients needing more expensive and dire treatments, these patients could get cheaper interventions early on.
What was the exact, and it's the reason I'm asking is it's, AI models to identify high-risk progression that idea has been around for a very, very, very long time. And it's the interventions that is actually generated. The tough thing is how to actually translate that to interventions that actually make a difference and also can be done on a large structure. For instance, like the electronic alerts for AKI, there's been
Yeah,
like 3 randomized studies for that. And all it really generated is alert fatigue.
yeah,
None of the studies actually showed that it made any difference. And one case actually showed a slight signal towards harm.
yeah,
So I'm like,
yeah,
so I think here the value is probably less in the actual prediction, but how they manage to couple it to intervention.
yeah. No, I
Also,
was,
the other pieces is just from a cost effectiveness analysis and health economics point of view, anytime you see a intervention claiming that amount of savings, um, it really raises eyebrows.
yeah,
You need to, well, I will say that the current surrogate that exists for identifying rapid progression is GFR slope, which is really hard to operationalize in clinical practice. None of us can sit there and plot that, and none of us know whether the last value that we see that creates that eGFR slope is going not to be different the next time. And so how true is that for that patient? So having something that can classify people is likely helpful, not helpful to this extent, unlikely.
that's
Because
what they said in
clinicians are likely identifying some of these people and treating them. And we do now have therapies that allow us to delay progression substantially. But and this is why it's important for us to sniff test and know what is in this model. And when you cannot tell us that, then we have alert fatigue, because we're like, we don't trust this model and we don't know what's in it.
Yeah.
Therefore, we're not going to use
Yeah.
it,
Yeah, no, I was actually gonna talk about that actual case. So I have another slide on how applying it is actually can be bad. But this was just something I saw in the literature and it was helpful. So this is a successful example of how they did it. And I remember there are details of what treatments they used, et cetera. But yeah, so you guys brought up some good points and we're gonna talk more about them. So yeah, AKI and AI. So one of the first examples we have is they used machine learning to predict AKI after cardiac surgery. And this was in South Korea. And they found XGBoost was the best model here. And you can see the values, but something interesting here is this plot, right? The ROC AUC curve, you can see all the models. I want to ask if people, not you, because you saw what was wrong with it. Does anyone notice if there's something wrong with this plot? Since we're behind, I'm giving 30 seconds. If no one gets it, I'm going.
Specificity and one lines.
Yeah, they're doing specificity and specificity. It's supposed to be sensitivity. Yeah, so the plot should look like this. But basically, yeah, it's supposed to be, and they spelled it wrong too. So this got published. 1 minus specificity, so the false positive rate, and sensitivity, true positive rate. Just a fun exercise. And they basically plot it at different thresholds. So the models have different thresholds. If you have a higher threshold, it's gonna predict less people. It's gonna have less recall. If you have a lower threshold, it's just gonna predict everyone. So that's why you plot it throughout different thresholds and get that area under the curve. And we see that gradient boosting was the best model here. So that was kind of the point. And this is the features they use in their model, the best features. So this feature right here, the intraoperable red blood cell count, I think was the most important one. It had the most weight. And this is just to show that a lot of these models have explainable features, and you can see what is the most important thing that the models are using to predict things. And yeah, so this is another thing for predicting AKIs. And I believe, oh yeah, this was at the VA, not this VA, just another VA. And they basically, instead of for patients undergoing cardiac surgery, it's just every patient that was admitted into the hospital. And this is kind of the design of the study. They had all their a longer history and they had the initial data when they were there, and then they would predict if they would get an AKI. This is the RLC curve. But the point is they use a recurrent neural network. So this is an example of deep learning because they had 700,000 patients. They predicted AKI in 55% of the cases and 92% of the more severe cases that required dialysis. So it could predict 48 hours before dialysis, but it had a pretty high false positive rate. And it's also not very generalizable because of the VA, it had almost all male individuals. So another group in also, I think, South Korea, if I'm not wrong, I think South Korea has a lot of these studies going on. They did kind of the same thing, but in their hospital system, and they got pretty good results. Notice that the XGBoost model is almost very comparable to the neural network. So it's not always the neural network, even the XGBoost is good. And we'll see later on, even logistic regression can be better than both of these. Yeah, so implementing these in the clinic, as you guys talked about, a couple of studies have been done that they basically implemented these as alerts. One of them found a reduction, but another one found no reduction at all. And like you said, sometimes there's an increase in time that you're spending in the hospital. So that's the question. The main question, which is actually more important, almost as important as the model, is how do you apply them? Because there's thousands of models with perfect ROC curves, perfect F1 scores, but they'll do nothing in the clinic. And it's a really important question that people are trying to handle. And at Stanford, we have the HARP team, right? And that's led by Dr. Stephen Lin. I actually met him and he said, like, while many AI models they get approached with are so good in publication, when they put it in the clinic, there's almost no use. So I feel like that's why as clinicians, we need to understand both sides of things and see how can we apply these on patients? Like, how could we actually benefit from this? Who cares about XGBoost versus random forest? Can we even use this in the first place? So this is an important question that I wanted, important point I wanted to raise.
So did he say anything of why, like, what is in the implementation part that is failing? Like,
So I talked to him, it wasn't, I just met him, and he's actually the person who helped implement AI Scribe. They don't make the tools, they analyze the tools. So they're not very technical, but they analyze the tools. And I guess because he's a primary care physician, he's the head of primary care here, he understands a lot about patient care, he understands what patients need, what physicians need, and he just kind of acts on his knowledge to see, okay, is this model going to be beneficial? Like AI Scribe, like they also run clinical trials, so they get these tools from Microsoft, Google, and they implement it in small settings, and they see, are the clinicians benefiting, are the patients benefiting, and he's kind of that guy who figures that out.
Yeah, I think it's, I think here you kind of presented two like case studies here. So something not less useful or that most studies have found to not be useful are EHR alerts. Something that just pops up and says, this patient's at high risk for, etc. That's it. Because in EHR Epic, as everyone here knows, there are a million alerts and we just click next, 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 next. That's the alarm fatigue.
Yeah.
And the one thing
And some of them, I'll say, some of them say your patient's gonna die in the next 24 hours because they're septic and the patient doesn't die. So yeah, that creates a lot of distrust and
Okay.
fatigue.
yeah,
Right.
or that says the patient's gonna die and you're like, no shit, I'm coding the patient right.
Right, that's the other option.
Like I could have
But-
told you that. Not helpful as I'm trying to put in some like stat order.
Right.
But,
I
like,
actually have never mind. I had a question. So don't they put these models under surveillance? Like after a while, when the doctors are
And then
saying
they
next,
retire.
next.
Yeah, then they retire those models
Okay,
later.
that's fine.
And so, but then what happens
The
is
new
when
one
the
comes.
next model
Oh, okay,
comes,
another one comes in.
there's a learned behavior from the prior model that carries through. Right,
Yeah,
there was.
Sounds like we almost need a QI study of how to work with these things.
yeah, the
It's
one
not
thing
big,
though
big
that
stamp.
you did present that's useful is the stroke model. And that one, just as can you go back to that page? Because I think there you on your slide, you actually outlined very nicely why that model works. So first of all, it's, yeah, this one. So first of all, it's, the condition. This is where every minute counts. So it's So it's like perfect for actual kind of AI use because it doesn't rely on someone manually reviewing it. It just tells it in real time. The second thing is an AI agent. It sends an alert directly to the stroke care team. It doesn't just, come out with an alert on EHR for the poor ED physician who's already overwhelmed and doing a million things. It alerts the stroke team directly, and it allows the stroke team to pull up the image immediately and decide, okay, this is like a real one, let's go, versus, I don't actually think so. I'm gonna cancel this alert and, go do the actual consult. So I think here it's the key thing is this is an actual agent. It's doing something that the ER physician or whoever ordered the CT would have had to do anyways, and it bypasses the radiologist who needs to page the ordering physician and the ordering physician who needs to call the stroke team. Actually bypasses two people at least in that step and gets the right people notified and shares the images. So I don't know. I think this tool is really cool.
Yeah, and it's also because models are so good at this, like
Right.
it's not as like a big deal because the model's most likely right. And so once models get so good, then you'll start to take them more seriously.
But this is not, the other caveat, I agree that this is helpful, and partly because it's targeted and actionable, it's not to everyone who is then, like, as a kidney doctor, I don't care, like, this is happening, but, the other part is it's not really doing new discovery that we cannot trust. It's taking an image and saying, is there a large vessel exclusion? Yes or no? It's a very simple efficiency gain. So that is helpful for it as well, because if it said that I took all of this electronic health record data and then I'm telling you this patient's going to progress to end state, then I would be like, well, what data? What are the features? And is this really going to hold up? But if this is just looking at one thing and saying, this is what I've seen, I think then it's easier for us to grasp and
It sounds like it also-
review.
It also sounds like it requires some part of human intervention.
Because
Or like
you have to-
evaluating.
Yeah, you get the notification.
Right,
You see
so
that.
it's not trying to operate on its own.
Well, yeah, you have to have the human in the loop for now. All right, let's.
But it's also like the benefit is seen almost like within minutes, right? Because if the stroke is about to happen, you would.
Yeah, you need it.
You would see it,
Mhm.
right? So it's not something like, well, you're doing that is something that's going to happen in the
Future, yeah,
years,
yeah,
right?
not
It's
good at
really
predicting.
immediate. And it's
Mhm.
simple, like the more complex you make it, the less we're able to fact check it,
Yeah.
in real time.
Yeah.
Okay, great discussion, but I need.
Yeah,
A lot of
Yusuf
stuff.
has read a lot.
So basically we have, I think this is a great example of unsupervised learning, and they use deep learning at the same time. So these are sepsis patients with AKI, and they wanted to see, they wanted to explore it, right? So you have this study, they had the sepsis plus AKI, and then what they did is they actually, firstly, they used deep learning to auto encode the data, which is basically they had like 2,500 features, right? And all these lab values, et cetera, and they wanted to bring it down to a handful of features. So what they did is they used deep learning to find which features are related, and they brought it down so they could feed it into more simple models. And then, so after they did that, they used k-means, which is an unsupervised method of clustering, and they got this. So just to explain this, you have a t-SNE plot, and if I had my notes, I would remember the acronym. But basically, it's an unsupervised method just for plotting. It doesn't have any significance, like you can't look at it and be like, yes, they have this, right? But the subphenotypes are generated by the k-means. So the plot is by another unsupervised method just for visualizing, and the blue and the orange and the green is generated by another unsupervised model that actually generates clusters. And so they found these three phenotypes in these patients, and yeah, and so they had different aspects, et cetera. So it's interesting, and this is used a lot with many different diseases to find subphenotypes of diseases. So now we're going to go on to AI analysis. Just one slide here. Pretty cool. This hospital in Taiwan developed a real-time AI prediction for kidney patients. And they use deep learning for this. And these are for patients for the risk of heart failure. And it's constantly has a dashboard with all these patients. And if someone is under risk, it will show like the red or whatever, and the clinicians will be notified instantly. So it's pretty cool. This is actually not published. I don't know why they didn't publish. It's just an NVIDIA article and it's in the news, but I don't think they published it for us to see what they actually did with their model. But very interesting real world application. Now we're gonna go to LLMs in nephrology. So there's so many different applications of LLMs you see in medicine. This was something pretty cool. They they used GPT-4 on 100 simulated patients to see how good it is in triaging, and it was almost 99 to 100% accurate in triaging patients to the right subspecialty. And I think this is like a really good application of AI. Just a tangent, like I've had ideas about like, I don't know, not a company, but like imagine like if the patient could just talk to AI initially and you could get rid of certain steps that you have to do in the hospital, like consulting, et cetera, and just send them to the right physician, right? So, but yeah, so it was really good at that. That's one application of LLMs. There's so many different applications of LLMs in medicine, as you guys have seen.
Maybe someone would be willing, but do you think your grandmother would be willing to chat with the AI?
I have one grandma and she's like 90 or 89 and I don't think she's in Iran right now. And yeah, if you show her ChatGPT, she might like have a heart attack. So, yeah, maybe let's leave my grandma out of it. But, yeah, so AI in health disparities. This is something I did last summer with Dr. Atul Bute, and we made machine learning models to predict vaccine response, and we tried to use a more diverse population. But the whole point is these models, they're as good as their data, right? And if you train them on all white people or all people from one place or another place, they're gonna not be generalizable. They're not gonna be good. And actually, there was like in Stanford Durham, actually, they did a really good job with this. They retrained one of, I think, Google's model that was a Durham AI model that was okay, but it was really bad at people of color. And they retrained it on a data set with more people of color, and it became good. And it was even better than the clinicians. And that's how actually, that's one thing. Is like I think humans are like AI because the clinicians who don't see patients from certain backgrounds, they're bad at it. It's in the studies, right? So we're just like AI. We need to see good patients. We need to see every type of patient so we can get it. So this was an interesting thing. I think is really important to me, getting equitable models. And this is kind of outline of all the challenges, right? There's so many challenges. I think one of the main ones we think of is when it comes to applying and doing it is PHI data and HIPAA, right? You can't just take data from everyone. You have to be careful on how you're applying it. And there's so many issues, like especially in pathology, like they have all these models, but they can't integrate it into the system because they're afraid of this. And there's obviously the generalization that we talked about. If you train it on a skewed data set, data quality is the most important. And then the black box is like with these super complicated models, it's like, okay, it's doing good, but you have no idea why. So these are kind of the challenges that I think we should all be aware about. And okay, so I'm pretty much done with most of the part. This is a presentation. This is supposed to be me. I made this with AI, of course, and this was a presentation I did in our group earlier where I talked about the things I use to learn AI and how I use AI to learn. I used it all throughout M1. I did very, very well just using ChatGPT, and I've been using it to learn how to code, learn everything. And here are some resources if you guys are interested to learn about AI. Dr. Langlois, he's the head of AIME. He wrote a blog and it has a lot of really good courses in Coursera, etc., and just advice on how to get started in AI depending on your level. There's this YouTube channel called StatQuest. It's so good. It's like, it's literally so good. Yeah, it's so good. Like if you don't understand a model, just search the model in StatQuest, and this guy will literally show a beautiful visualization with real numbers, real world examples, step by step for you to understand the model. So it's good for all levels, and just AI itself. My pipeline is I feel like I'm an AI agent because I'm just asking AI every time I don't know something, and that's kind of what I'm doing. And there's so many other resources. Please feel free to reach out to me. I'd love to talk more about it. And I made a website from this presentation because It's just.
Because you know.
Yeah, because I can.
We need it. So that's first.
So I can share this website, but it basically, this is AI generated, of course. And this is not as updated as everything I have in my presentation. I basically fed it a couple of review papers that have a lot of interesting stuff about AI and nephrology. And yeah, this is my works cited. Oh. Thank you. It's an amazing.
Oh my God, you replaced us.
Yeah, so I made that before doing the presentation, so it could have gone horribly. I hope it went well. And that's kind of the whole presentation. And if you want to connect with me, these are some information about me. So yeah, that's the presentation. Thank you. And yeah, so if there's any questions or comments, I'll feel free to take them. There's also,
Sites in the chat. I was trying.
I'll share this presentation. There's also like 2 or 3 slides about how I made the website that would take 2 minutes. If people are interested, I can share it. If not, I'll just do it there. We have 5 minutes. Should I share them?
Sure, yeah.
Okay. Basically I made my own personal website, which you guys saw in the first slide, and it's pretty good. And so this is how I did it. So you just go to Gemini. Firstly, if you have an EDU email, you get Gemini for free. So for 1 year, so do that. It's so good. And then I put my CV, I put a bunch of stuff. I'm like, I want to make a website, right? It gave me some code and it gave me a website, but I didn't like it as much. So what I do, I copied my cousin's website, who's a software engineer, and I was like, I want to copy his website and show him that I can make a website like him without knowing like all the intricacies behind React.js and all this stuff that these software engineers use. I did that, and what it did is it gave me some code. It gave me, you can preview the code and you can run the code there. Don't mind the one, I was just playing around with the code, so you can edit the code here. And yeah, so it gave me a pretty good website. It's not perfect, you have to make some changes if you want it to be perfect. And then what I did was I just uploaded it to GitHub and I hosted it on Vercel. And what you see here is like kind of my website. It looks pretty professional. And this was made in 15 minutes, genuinely 15 minutes. This would have taken days before, and you would have had to pay someone to make this. And it's good because you have the code. You're not using Wix. Like you don't have to like go and do all this stuff. Like you can just edit whatever you want, whenever you want. And whenever you Google your name, the first thing will be your website. It'll look super cool, and people will think you're so amazing because you have your own website. So yeah, that's what I did. And this would be its own talk if I wanted to go into details of it. But I just wanted to share this. Oh. Wait. So that might have seemed really random to you, but if you're on TikTok or something, you've seen like there's a trend of like Bigfoots. Like people are taking videos of Bigfoot and they're like just making funny videos about it, like just Bigfoot like just going camping or like drinking Starbucks or something, and they're using VO3.
Do you
So
want to try it?
yeah, so yeah, that was